So about 5 years ago, I made a series of videos on optimizing 3D games in GameMaker, and one of the things that I covered back then was combining vertex buffers into a single vertex buffer. This would allow you to do things like drawing, like fusing all of the static objects in your scene into a single model, and allowing you to draw them all in one shot. That generally works out all right, but there is a particular limitation that comes about when you do that, which is that it only really works if all of your vertex buffers are using the same texture. Because if you try to combine a bunch of different vertex buffers that each point to different UVs on different texture pages, then weird stuff is going to happen. And it was about 5 seconds after that video was posted that people started asking me how you can do the same thing on vertex buffers with different textures. And now it's almost 5 years later, and here we are. That's what we're going to do today. So, there's a couple of things I should probably go through before I make any changes to the code. So, one of them is why actually it took 5 years to make this video. And there's a couple different answers to that. The first one is that there's a lot more moving parts to this than there are in a lot of the other optimizations that I talked about way back then. What we're going to do today to fuse a bunch of different vertex buffers into different, which use different textures into a single vertex buffer, we're going to have to combine the textures into a single texture atlas. And I suppose if you really want to, you could stage multiple textures and index each of the vertices in the tree so that you know which texture to read off of. I'm not going to do that. That's dumb and boring. We're going to go with the texture atlasing route. Speaking of which, there is a reason that I made several videos a couple months ago talking about texture atlasing. And if you haven't gone and watched those videos, I would recommend going and doing that, because we are going to be making use of the code that I wrote back then. I will not be retreading old ground here, and it's going to be fairly core to what we're doing. So the second reason that it took me almost 5 years to make this video is that I don't actually like this optimization that much. I think it's rather situational, and it's not the panacea that a lot of people seem to think it is. And to be fair to the merging different textures thing, a lot of the problems with doing this are also present in the merging vertex buffers that use a single texture. And I probably should have hammered that point home a little bit harder than I did back then. But there are better and worse ways of implementing something like this. There are definitely situations where you might go to all the effort of fusing all the geometry in your scene into a single vertex buffer, and it doesn't really make that much of a difference if that's not actually where your bottleneck is. Depending on how exactly you go about doing this, it is possible that you could lock yourself out of other optimizations that might be better optimizations. And we're going to talk all about that as we progress in this video. I am going to start off by kind of doing this in a bad way on purpose so that we could see what kind of a difference it makes to do it, better. So, by the way, I probably should have played this game with the other optimization videos that I did, because it's kind of fun to see what people think. But before you watch any further, I want you all to go down into the comments, and I want you to give me your predictions for what kind of frame rate improvements we'll see by merging all the tree models in this forest into one. So that's that. Let me actually go and talk about what these tree models are real quick. So this is a different tree model than the one that I was using earlier in this series. This tree model actually has textures on it. It's not just vertex color like I think a lot of the ones I was using earlier were. I got this off of OpenGameArt. I'll have a link to it down below if you want to go and play with it yourself. I think it was originally made for like a Quake 3 mapping competition or something, which is why it looks like something out of the early 2000s. Anyway, there are two different vertex buffers in this tree model. So there is one that is going to contain like the leaf textures, and we can see that there's a couple different leaf textures. And there's also a separate vertex buffer which is going to contain the trunk and the bark texture. And for every tree in the scene, we are drawing two vertex buffers, one for the bark and one for the leaves. And that is resulting in 30,000 trees times two vertex buffers per tree is 60,000 individual vertex submits. And that's a big number. The end result of that is that we're getting about 30 FPS, about like 40-ish FPS underscore real. FPS underscore real is not going to be an important number to us today. Don't look at it. And I am curious to see what kind of a speed up people expect that we'll be able to see by fusing the tree models in the scene together. And there are a couple different acceptable answers to this question. There's a couple different ways that I'm going to be going about merging all these things together, and we're going to have some fun with this. I am running this on a somewhat larger computer than I was when I did the original 3D optimization demos. I'm running this on a Ryzen 9 9950X and an Intel Arc B570, whereas the older optimization videos that I was making were on a some combination of a Raspberry Pi 5 and a Intel i7 7700 and a short GTX 1060. And if you do want to run this demo yourself, I would recommend being a little bit careful about the tree count here, because like if you're running this on an older computer or on a laptop or something like that, I don't want to be responsible for setting your desk on fire. So maybe dial down the tree count just a little bit before you go and do that. All right, I think that's the whole preamble. Let's get into modifying the code. So I have made some modifications to the original combining vertex buffers demo. There is code for doing exactly that. I have modified it in some ways since the original version, partially because GameMaker gave us some new features which allow us to more easily like transform the positions and normals of vertices without having to do it like in a somewhat more expensive way. And partially so that we can actually make use of the different like the individual vertex buffers for a trunk and leaves and that sort of thing. So there are 30,000 tree models. They are randomly scattered over a range of, well, this. They're given a random scale, a random rotation, just to keep things fun. And then in the draw event, as you might have seen earlier, we're just going to iterate over that trees array and then submit the bark and the leaves separately. There is still code, and I'll make use of it here just to give us something to start with, which is going to combine those into a single vertex buffer. And you can probably imagine off the bat what kind of a problem we're going to run into when we do this. Possibly even several problems that we'll run into. One of them being that, like, when you're trying to draw a single vertex buffer that's comprised of vertex buffers that use different textures, what texture do you actually assign to it? And that's going to be a fun question that we'll get to in a minute, but for the time being, I just hard-coded it to be the bark texture. And I think now I can just run the game, and we can see exactly what this looks like. So the first thing you'll notice when you run the game, before the game window even appears, is just how long this takes. And I think in my testing, this took about 70 seconds to combine all these tree vertex buffers into a single vertex buffer, all 50 million vertices that we're going to have to loop through and transform here. So that's obviously going to take a little while. And I'm going to try and just talk through the time interval, because I want you to really feel how long 70 seconds is when you're waiting for something to happen. And there are definitely some obvious problems with this, like, again, before the game has even started. And there are also ways that we will be able to address this particular problem of loading time later on in the video. Is there anything else that I really want to go over here? Let's see. I can't remember if this was in the original video or if this was a modification that I made later. There was also a problem in the vertex buffer add buffer function where there was a memory leak because we were creating a buffer from a vertex buffer and then not deleting it when we were done. But I think that might have been a modification that I made later after the original video that wasn't in that one. So that's just I got rid of that. I'm creating this from the source buffer without using the vertex buffer as an intermediate. I think that finally finished, and that took 71.42 seconds to crunch through all those. And we can see, oh, you know what's happening? I forgot to comment out the loop where I, like, draw the original trees. Meaning that both are going to be drawn, which means that this whole thing is actually going to be way slower instead of faster. Let me comment that out and sit through another 70 seconds of nothing happening. Alright, much better. So, another 70 seconds later, and we can see that something definitely looks wrong with all these trees. Which is unfortunate. They look kind of dead, and that's because we are using the bark texture for, like, the trunks and stuff. So, let's see, how does this look? We are seeing 116 FPS and some number that doesn't really mean anything, FPS underscore real. We are down from 60,000 vertex patches and texture swaps per frame to 3 vertex patches and texture swaps per frame, and that's definitely a step in the right direction. If I move around, the game does feel a lot smoother, although I don't really think that like the trade-off in performance for each of these trees using the wrong texture is really worth it. But I wanted to do this just so that we can more or less get a performance metric and see how performance might be improved by, you know, doing all this. Alright. Boy, especially the fact that the bark textures don't have, like alpha cutout and, like, the space between leaves just looks black. That looks really, like, weird, uncanny, kind of horrible. I'd like to get that off my screen. Alright. 116-ish FPS. We'll see if we can maintain some level of performance like that, and also deal with the problem of having textures that need to like be applied correctly. So the way that I'm going to apply textures correctly is I'm going to take the Sprite Atlasing code that we wrote a couple of videos ago, and if you might remember that there were three and a half different Sprite Atlasing algorithms that I wrote. You can pick which one you want to use. It probably doesn't matter that much. Generally, when you're working with textures in 3D, you're not going to be dealing with textures of all kinds of crazy different sizes. They're probably going to be like, you know, something power of 2 like this, 256 by 256, or 1024, 1024, or 4K by 4K if you're feeling fancy. I'm going to go and grab Pack Sprite's V3A as my my texture atlasing algorithm of choice that I'm going to use in this demo. It's probably the mostly like broadly applicable one. So let me go and get it out of the Sprite Atlasing project by going and saying create local package. And I'm just going to call it Atlas. And I'm going to include the placeholder Sprite object, Sprite end object in the actual code that we need to run this. I'm just going to go and export that, and I'm going to save it to like my user folder or something. And GameMaker ever finishes running this, we can open that file in Explorer. I can go back into my main project that I'm actually working in here. I can take atlas.yyMPS, I can drag and drop that into the IDE, and we can transfer the assets from that project over here. So to atlas the sprites, to put all of these textures that are going to be used by these trees onto a single sprite atlas, I'm going to want to go and create an array. Let's call it texture sprites equals an array, and I'm going to put the two bark textures and the three leaf textures in that array. And I'm going to call pack sprites v3a. Apparently code help didn't really want to help me there. Pack sprites v3a. And this is going to just take an array of sprites like that, which we just created. And it's going to put them into a single... it's going to create a new sprite with all the input sprites arranged nice and neatly, with minimal space between sprites and without any like overlaps or anything like that. I can save our atlas. Let's call it atlas info equals pack sprites v3a. What exactly this is going to return? This is going to return a struct containing the sprite itself, which we created, and also an array of metadata for each of the sprites that went into it. And I think I'm actually going to make a modification to this, because this is something that I kind of didn't see coming when I made the original, which is that in addition to the x, y, width, and height of each sprite being contained in the sprite metadata array, it probably wouldn't be a terrible idea to have the u and v coordinates of where each sprite, like, where its bounding rectangle on the atlas is, because that's going to be something that we're going to need to know when we combine these and when we combine the vertex buffers. It's not something that actually, like, is present here, and I would like it to be. So I think in the when we loop over the atlas at the bottom, we have sprite info equals sprite rex index I. This is going to be the struct with the x, y, width, height information. I think I'm going to say sprite info.u1 equals sprite info.x divided by, what is it, surface get, oh no, it's just atlas width. I think I can just use that. So u1 is going to be sprite info.x divided by atlas width. Sprite info.v1 equals sprite info.y divided by atlas height. Sprite info.u2, which is going to be the rightmost side of the sprite, is going to be sprite info.x plus sprite info.w divided by atlas width. And I'm just going to copy and paste this because I don't feel like writing out the same thing so many times. Sprite info.y plus sprite info.h divided by atlas height, like that. So now each of the little bits of sprite metadata now also know exactly like where they are in texture space as well as in pixel space. All right. Feather is yelling at me for something here. I don't really know why. Sometimes like typing something, saving, and then backspacing whatever you typed makes it go away. Feather, for the most part nowadays, is pretty good, but once in a while it will do something weird like that. Anyway, that is going to be our texture atlas. If you want to see exactly what that looks like, I'm going to comment out the vertex combine, because I don't really want to sit there for another 70 seconds waiting for it to run. I'm going to go comment out the code that would crash if it expected to see vertex buffer that doesn't exist. And I'm going to just run this in debug mode so that we can see the sprite atlas texture and see if it worked correctly. It is now really, like, weird when I'm getting effectively infinite FPS to, like, see how quickly the response time is when I move the mouse down there. Anyway, let me go and pause the game in the debugger. Let me go over to the graphics tab down here, and if I were to hit the little refresh button, that's going to allow us to actually see what each of the individual textures are in here. So we've got the original, like, leaves and the original bark and what have you. And down here, this is the combined texture. So this is what the result of that texture packing function is going to spit out. So we've got the two larger bark textures. Those are 512 by 512, and the three smaller leaf textures at 256 by 256. And they're all packed together nice and neatly into that rectangle. So that, I'm pleased to see, did exactly what it was supposed to. So now that we've got the texture atlasing out of the way, let me actually go and make use of that inside the vertex buffer combine code. So I'm going to have to go and make some modifications to vertex buffer add buffer. Let me go and Control-D duplicate vertex buffer add buffer, and I'm going to rename it vertex buffer add buffer atlas or something like that. And we're going to go and call this instead of calling the original version, which didn't account for texture pages or anything like that. And we're going to need to pass a little bit of extra information to this vertex buffer add buffer atlas function. So the information that I'm going to give it is, one, the actual texture, because we're going to need to know that at some point. That can just be tree.bark is going to be a reference to the sprite, which is used as the bark texture, and tree.leaves, which is going to be a reference to the sprite that is used as the leaves texture. I'm going to also need the atlas info. So the sprite atlas info, and I'm actually going to not make this a local variable because I will want a reference to that to hang around. I'm going to specifically, I need the atlas info array, so I don't need the sprite atlas itself, the master texture that everything ended up on. I just need the array of metadata. So I think I'll just say .atlasinfo.metadata like that, and that can be the second argument that we're going to pass to this vertex buffer add buffer atlas function. So now, let's go and make the modifications that we need to here. So this is going to take a couple of extra arguments. Texture, sprite texture, let's call it, and the atlas metadata is going to be the other one. So what we actually specifically need, and not the sprite texture itself, is we need to be able to figure out which one of these pieces of metadata belong to the sprite. And there's a couple ways that you can put this logic together. There's a couple different ways that you can, like, index the sprites so that you can just, like, look them up in constant time without having to basically search the array. I am just going to do this the naive way and search the array. And we can say, actually, before I write a loop, var sprite metadata equals undefined. For I equals 0, I is less than array length. Atlas metadata I++. We can say if atlas metadata index I dot sprite, because each of these pieces of metadata do also contain a reference back to the original sprite. If that dot sprite equals sprite texture, then sprite metadata equals atlas metadata index I, and we can break out of the loop because we found what we're looking for. We don't have to search any farther. And again, there are other ways that you can do this. I know that people are going to offer alternatives in the comments, some of which might or might not be more efficient. I am just going to leave that as it is. All right, so I think that is... Yeah, I think that's all I need to do to get the sprite metadata. So this is going to contain, like, the x, y, width, height, u, v coordinates of each sprite on the texture page. And now comes the fun part of actually adjusting the texture coordinates, xt, yt, x texture, y texture, uv, whatever you want to call them. We're going to have to adjust the texture coordinates for each vertex buffer when we write it to the combined vertex buffer. And it's actually really convenient to do this because you could write some code to like remap and scale the values and offset them by some amount to go from a range of 0 to 1 to a range of u1 v1 uv v2 on the new texture page. You can write out that arithmetic yourself, or you can use the lerp function for this, and the lerp function will do basically that just for you automatically. And we can say, let's lerp from sprite metadata.u1 sprite metadata.u2, and the amount that we can lerp between these two values on the sprite atlas texture page is going to be xt, and we can reassign xt equals that so that that value gets updated with the updated texture coordinates. And we can do the same thing with the vertical texture coordinates. So yt equals sprite metadata dot v1 v2 lerped by yt. And the reason that this works is that the x and y texture coordinates are going to be in a range of 0 to 1. When you like lerp from one value to another, you're generally going to use a lerp factor of something between 0 and 1, with 0 being the smaller value and 1 being the larger value. You can, of course, go outside that range if you want to extrapolate instead of interpolate. But that is not what we're going to do here. I guess it is worth mentioning that if you're using texture repetition here, this isn't going to work. And you're going to have to either cut up your vertices so that they don't use texture repetition, or just not do this. Anyway, once we've had our fun with that, we can just use these modified values when we write data to our combined vertex buffer. And I think with that, it is time to make those feather warning messages go away, and time for me to run the game again and wait another 70 seconds to see exactly what this comes out looking like. Alright, and once again, as I did the last time, I forgot to do something before running that. And that means that I'm going to have to sit here for another 70 seconds. Out of curiosity, how long did that take? That took 78.25 seconds, so a little bit of extra time cost in doing this little remap operation here. There are ways that you can squeeze out a couple of individual like GameMaker operations every time this runs by, for example, indexing this in a more ideal way. But I think at the end of the day, we'd rather not have to sit here for 70 seconds anyway, so I'm not going to lose a lot of sleep over that. What I do need to lose sleep over, though, is when we go to actually draw our combined vertex buffer, instead of saying sprite get texture that, let us actually use the texture of the sprite atlas, which is going to be atlas info dot, I believe it's dot atlas. I like it when feather works correctly because it does know what type atlas info here is supposed to be, and it does actually correctly like give me the options of what variables are contained within it. But atlasinfo.atlas, that is going to be the sprite that we actually want to do here. Let me go and sit through another 70 seconds of this operation carrying out, and hopefully that'll be the last time before we move on to doing something about that. Alright, another 70 seconds has come and gone. We are now drawing the entire forest as a single vertex buffer, each using the correct textures. And we are now getting, instead of like 30 FPS, we're getting something like 115, 116 FPS. Hey. And I think it is now time that we address some of the other problems that are fairly obvious on display here. So the most obvious one is that like 70 something seconds that it took this to start. 78 seconds this time, apparently. That's a problem. It would be really great if we didn't actually have to do that. The second problem is that I mentioned at the beginning that when you do this, you kind of lock yourself out of a couple of other optimizations that might or might not actually be better than what we're doing. So at any given moment in the scene, we're probably not really seeing more than maybe 1,000 or 2,000 trees, if that, at any given moment. Most of the trees in the scene are going to be behind us or beyond the far clipping plane, so out of sight, too far away over the horizon. And when it comes to not drawing stuff that you obviously can't see, there's a couple of other optimizations that you can put to work here. One is going to be chunking. So chunking, you might be familiar with Minecraft, is the practice of like subdividing your world into sections and only drawing the sections, or in some cases like updating the sections in the step event. which are actually visible to you. It's kind of the whole, it's at least part of the whole, like, meme on social media about how in games, if you can't see it, it doesn't exist. It's more complicated than that, but that's the essence of it. And obviously, when the entire forest is being drawn as one vertex buffer, you can't really do that. You can't really just go to a vertex buffer and say, like, draw the stuff between these coordinates. That doesn't really make sense.
Hey.
In recent versions of GameMaker, you do have the option to only draw, like, a certain number of bytes in a vertex buffer, but that doesn't really help us here. The other thing you can do here is, instead of chunking your level, you can just actually only draw individual objects that are within view of the camera. This got a lot easier in recent versions of GameMaker with the addition of the sphere is visible function, which is the next thing that I'm going to be putting to work here. So let me close out of that, and let me go and comment out the combine code, because I don't want to sit there for another 70 seconds the next time I run the game. And if I comment that out, and if I go back to the step event, to the draw event, and let's see, comment that in, comment that out. If we go back to drawing each of our individual trees individually, we can use the sphere is visible function to see if if a sphere of a given size is actually visible to the camera. This function is going to take an XYZ and a radius, and it's going to return a true or a false. So the XYZ in our case is going to be the position of the tree. So in the tree data struct, which I've defined ahead of time, X, Y are given, the matrix is given, and the two textures are given. I'm just gonna say tree.xx, tree.x, tree.y, and the z is gonna be 0 because every one of these trees is just drawn on the floor. And the radius, I happen to know that I think the largest radius of any of these trees with the scale that we have is gonna be about 250. I'm just gonna hard code that. You should probably, if you're gonna do something like sphere is visible, keep track of what the bounding radius of an individual model is so that you can do this like programmatically, but I'm just going to hard code it. And I can say if sphere is visible, then we're going to draw all this. If not, if the sphere is not visible, then the thing is out of view anyway, we're not going to draw it. And if I run the game now, we're actually going to see probably a similar, okay, not quite better, but definitely a similar improvement to what we had before. And, alright, so it looks like there's actually a few more trees that are actually being drawn here than I was expecting. I was expecting like 2,000 or 3,000 trees to actually be in view at any given time. We do have a whole entire forest here, which is kind of an impractical number of trees to actually have on screen at once. And even here, like 30,000 trees, like at this scale, realistically, what you're going to do is like level streaming, and that's a whole separate... Alright, so apparently the bounding sphere is not quite big enough to encompass this guy down there. Realistically, if you're gonna have like a game world the size of like actually Skyrim, which I believe the most recent tree survey in Skyrim gave us about 44,000 trees, you're gonna have some sort of level streaming system so that not all these actually have to be loaded at the same time. But that's neither here nor there. Just by being smart about how we draw our trees and not combining anything, we're gonna get a boost to high 90s, low hundreds FPS, depending on exactly what we're looking at. If you look at, like, the sky, well, I guess you can't actually see that because of the floor. If you look, like, straight down, where there aren't many trees in view, our FPS is going to go up dramatically. Versus if we were to have, like, draw the whole combined buffer. If you look over at, like, in the direction of most of the level, it's going to drop off a little bit more because there are more trees off in that direction. But still much better than what we started with. Alright, so that's not strictly related to combining these vertex buffers. We are still here drawing 2 vertex buffers for each actual tree, and like if we cut that in half, we could theoretically cut in half the amount of time that it's going to take to at least draw like this, like the actual trees that are on screen. And that'll definitely give us some additional amount of performance boost, which I think most of you will be happy about. So let's think about combining each of the vertex buffers, not for the entire forest as a whole, but for each of the trees individually. So I'm not going to do a thing where I go and, like, for each tree, like, create a new combined vertex buffer for each tree, because that'll be a little bit ridiculous. Realistically, most of these are going to end up being, like, the same tree, and we're just going to be doing, like, duplicating a lot of work for no real reason. You could also, and this is going to be one of those things that you could do that would make this so much worse than if you just left it alone, but you could like combine the tree textures for each of the individual vertex buffers, and that would just basically create like a VRAM disaster. Don't do that. I'm not going to do that because VRAM is expensive and I don't want my PCIe bus to catch fire. So instead what I'm going to do is I'm going to look at the 6 permutations of these 3 leaf textures and 2 bark textures. I'm going to create a vertex buffer for each of these permutations. I'm going to map it to this texture atlas, this main texture atlas, and I'm going to attach the appropriate combined vertex buffer to each of the individual tree data, and I'm just going to draw that instead of drawing them separately, and that should give us a decent speed boost. So let's first let me make two new arrays, one for the bark textures and one for the leaf textures. Like that. And I'm going to create a, let's say a struct. Let's call it tree versions. And that's going to be an empty struct. And I'm going to iterate over both of these arrays, and I'm going to work out for every permutation, I'm going to create a new combined vertex buffer, which is going to look something like what we did down here. Let's see. Do I want to copy and paste this, or is it going to be easier to just rewrite it from scratch? I'm just going to rewrite it from scratch. So, var vb combine equals vertex create buffer. Vertex begin vb combine. Our vertex format is just going to be the one that we defined up here, position, normal, text, chord, and color. That one that we use for everything. I am going to vertex buffer add buffer atlas, and our destination buffer is going to be vb underscore combine. Our source is going to be not the vertex buffer for the trunk, but the one that we loaded from the disk. Again, that was a change that I made off screen just because it's a little bit fewer moving parts to keep track of. Our matrix is just going to be an identity matrix. We're not going to do any transforms here. And in fact, if you wanted to make a third version of this, which doesn't transform any of the coordinates when you do this, that will be slightly more efficient if you if not applying a transform as a concession that you're willing to make here. The sprite texture can be bark textures index I, leaf textures index J, and oh no, I don't want to do those both. The first one, we're going to do this twice. Bark textures index I. The atlas metadata is going to be atlas info dot metadata, and we can do this again for the leaves, and this is going to take the leaf textures index J, and that is going to give us a vertex buffer which contains both of these things. So when we're done, vertex end, vertex freeze, so that we can permanently stash away this vertex data in VRAM, and we don't have to copy it over to the GPU every time something's drawn. And lastly, I'm going to insert this into the tree versions struct as a lookup table, and I'm going to index it by, I think, using the name, the sprite get name of bark textures index I, comma, sprite get name of leaf textures index J. And this is the name. So this is going to be like SPR oak bark, comma, SPR oak leaf fall, or something like that. This is the name which we're going to be able to look up this vertex buffer in this struct with. And now down here, tree data index. You know what? I'll do this in line. Well, let me move out. Bark texture equals that, and var leaf texture equals that. Bark colon bark texture. leaf colon, leaf texture. And lastly, I'm going to just go and attach a vertex buffer to this tree data. Let's call it vbuff, the good old-fashioned way. And that is going to be looking up in this lookup table over here. The vertex buffer, which can be found at key with the name Sprite get name, bark texture, comma, Sprite get name, leaf texture. Like that. Alright, that is a lot of punctuation at the end of each of these lines. I don't know how to feel about that, but it's going to work. So, now that we've gone and created all 6 of our permutations and found the correct permutation to attach to each piece of tree data, we can actually go and draw that tree data. So instead of going and saying vertex submit vb trunk whatever, we can say vertex submit tree dot vbuff like this, and the sprite that we're going to use as our texture is going to be the atlas that we can bind like this. So atlas info.atlas. And for my own record keeping, let's go and vertex total plus equals vertex get number tree.vbuff. And that's going to allow us to keep track of how many vertices are being drawn each frame. Alright, I'm also just going to increase the radius here. Again, hard coding. Apparently 250 wasn't quite big enough for some of the trees, so gonna give it a bigger radius. You did not like that. Why did you not like that? Did I use the wrong array? Oh, bark texture, leaf texture, bark textures. Yeah. Probably should have picked variable names that are a little bit more different from that. So, that works. And we can now run this. We can see that we are now, instead of submitting like 14,000 vertex buffers for each of the, for like 7,000 trees, we're submitting half of that. And we're now getting considerably higher frame rates than we were before. We're still drawing like 12 million vertices, 4 million triangles, and we can see that if the exact performance figures that we get do still depend quite a lot on exactly how much is on screen. So if I look down at the ground where there aren't going to be quite as many trees being drawn, 49 trees apparently in this scene, we're going to be seeing much higher performance levels than we would be if we were looking at, you know, the vast expanse of the land where there are some 7,000 or so trees being drawn at any given time. And we are still losing some performance to just, if you were to look in the profiler, you would see that this whole loop here is accounting for a decent chunk of frame time. And again, if you were actually making a game that looks like this, you probably want to look into some sort of level chunking, level streaming system so that you don't have to, like, contain data for all 30,000 trees, even if a maximum of like 7,000 or 8,000 are only going to be visible at once. To me, at least, that I think is an acceptable compromise. You could compromise further by, you could, again, chunk things, and then you could combine, like, trees and individual chunks together, and then you could only draw trees that are, like, rather, instead of having to loop over 30,000 trees, you could just loop over, like, 100 chunks and figure out if those are in view or not. But I'm not going to go that far today. Maybe there's a future video to be made on that, but I feel like at this point you can probably figure out what that code is going to look like. Anyway, I'm going to end this off here. My name is Michael. I like Wizards and Dragons and making games. If you want the code for this, look for the GitHub repository down in the description of this video. You should all go check out Wizardex and the Lost Hat, which is one of the games that I like to work on when I'm not doing YouTube stuff. Link to the Steam page can be found down below. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Me saying that this video took like 5 years to come out is a little bit hyperbolic, but this is also like the 4th or 5th take of this video, because I didn't really like how the first few came out. These do take a lot of work to make. I hope you all found that useful, and I will see you all later. Special thanks to Zenjamin, Zach Robinson, Squarecrow, Spide Games, Pixelated Pope, Paradox, Manta Ray, GameMaker, Gamer Indie, Edward Holt, DJ Gibbles, Brenton, Bokeh Dev, and Arger the Naut for supporting these videos. If you would like to join these wonderful people, head on over to the Patreon page down in the video description to join the fun.